A single truck, late by 1 hour, arrives at a busy warehouse. Most people would see this as a minor inconvenience. It is a small problem, easily absorbed. Yet that single late truck can trigger a cascade of failures. A cascade that can bring an entire supply chain to its knees. A small delay is often not small at all. It is a signal. It is a test. It is the first tiny crack in a dam. This essay is about how that crack forms and spreads, turning a weight into a system-wide catastrophe. We see these as surprising failures, but they are often predictable outcomes of our systems. First, we examine the visible problem, then the hidden mechanism behind it, and finally, the system effect almost nobody sees coming. Imagine a busy grocery store on a Saturday afternoon. There are 5 checkout lanes, but only 4 are open. One of the 4 cashiers, a new trainee, is working much slower than the others. The line for that lane begins to grow. Soon, it snakes back into the aisles, blocking other shoppers. Customers become frustrated. Some abandon their carts and leave the store. The store manager sees the long line and the slow cashier. The obvious cause of the problem is the trainee. The obvious solution is to train them better, or move them to a less critical task. This seems like a complete explanation, but let's look closer. Why was a new trainee working a register alone during the busiest time of the week? Perhaps the store's scheduling software is designed to minimize labor costs, assigning the fewest possible employees to each shift. Why was the 5th checkout lane closed? Perhaps a policy to reduce operating expenses keeps it shut unless a certain number of customers are waiting. These are not problems with the cashier. They are problems with the system's design. The slow cashier was merely the trigger that exposed the system's underlying fragility and its focus on cost-cutting over customer experience. The obvious answer was not wrong, but it was dangerously incomplete. Consider air travel. A single flight is delayed by a thunderstorm. That seems like the clear cause for subsequent problems, but the real issue is how the airline system is structured. Airlines create schedules with very little slack time between flights for each plane. This is called high asset utilization, and it is very efficient. But when one flight is late, the plane is late for its next flight, and the one after that. The crew might also reach their legal work hour limit, forcing a crew swap that causes even more delays. The thunderstorm was the trigger, but the tightly packed schedule was the true cause of the cascading failure. If insights like these help you see systems more clearly, tap like, add a comment with your experience, and subscribe for our next breakdown. To truly understand how a small delay grows, we must follow its journey through a system. Let's use a simple example. A pizza delivery shop. Phone call. Kitchen. Driver. Customer. The visible problem starts when one driver, let's call him Alex, gets a flat tire. This is the trigger. The obvious effect is that a few customers will get their pizza late. It seems contained. The shop's system has hidden connections and constraints that will now come into play, turning Alex's flat tire into a much larger problem. The first hidden mechanism is dependency. Other parts of the system were waiting for Alex to return. The dispatcher was waiting to give him his next set of orders. The kitchen staff, seeing orders pile up, might slow down to avoid pizzas getting cold. Now, the delay has spread from one driver to the dispatch and the kitchen. The shop's overall capacity has just been reduced. What was once a problem for 3 customers is now a problem for all future customers. Next, the delay encounters a threshold. The shop has a promise, delivery in 30 minutes or less. For the first 15 minutes, the system might cope. Other drivers might take one of his orders. But as the delay crosses 20 minutes, a threshold is passed. The remaining drivers are too busy to help. The pile of waiting orders becomes too large. The dispatcher must start calling customers about a significant delay. This action consumes more of the dispatcher's time, slowing down new assignments. Finally, a feedback loop kicks in. As more customers are told about the delay, some cancel. This seems like it might help, but the kitchen had already made those pizzas. Now, the shop has wasted food and lost revenue. To make up for the loss, the manager might push the remaining staff to work even faster. This pressure can lead to mistakes, wrong toppings, incorrect addresses, which create new delays and more unhappy customers. Alex's single flat tire has now triggered a spiral of interconnected problems that degrade the performance of the entire shop for the rest of the night. Every system operates within limits. On a normal day, when traffic is flowing at 70% of capacity, a minor accident can be cleared with only a small slowdown. But during rush hour, when traffic is at 95% of capacity, that same minor accident can cause a massive traffic jam that lasts for hours. When a system operates too close to its maximum capacity, it loses its ability to absorb shocks. Small delays don't just add up, they multiply. The system becomes brittle. To protect against this brittleness, systems can be designed with buffers, reserves that absorb unexpected loads. In a factory, a buffer might be extra parts that keep the line running despite a late shipment. In a hospital, a buffer might be a few empty beds to handle a sudden influx of patients. Buffers provide resilience, the shock absorbers of a system. The problem is that buffers are often seen as inefficient, money sitting on a shelf. In the pursuit of efficiency, many organizations remove buffers and adopt just-in-time manufacturing, where parts arrive exactly when needed. They aim for 100% occupancy and high utilization. It looks excellent on paper, as long as everything runs perfectly. By removing slack, we optimize for a perfect world, but become fragile in the real world. When the inevitable small delay occurs, a late shipment, a breakdown, a demand surge, there is no longer a buffer to absorb it. The shock is transmitted and begins to cascade. The quest for efficiency, ironically, makes the system more prone to collapse. Systems are made of people, and people respond to incentives. A focus on narrow, easily measured targets can undermine the whole system. Consider a call center. A common metric is average handle time. Agents are rewarded for keeping calls short. When a customer has a complex problem, an agent pressured for speed might give an incomplete solution. The customer calls back later, adding to the queue and increasing wait times for everyone. The agent met their goal, but the system got worse. At a port, incentives to unload fast can lead to disorganized stacks that slow down trucks later. A delay is shifted from ship to trucks, where it becomes a bigger bottleneck. A manager paid to minimize inventory hesitates to order extra supplies despite looming shortages. A pilot measured on on-time departures might rush checks and miss a small issue that becomes a larger delay later. Each person acts rationally within their rewards, but the result is a system that sacrifices resilience for the illusion of local efficiency. Delays are not just technical events, they are social phenomena, magnified by human choices. The incentives we create can amplify small delays into major failures. Delays do not grow in a straight line. Their behavior is governed by thresholds and feedback loops. Below a threshold, systems cope. A short delay is manageable. Cross a threshold, say 4 inches of snow, and safety rules trigger. Fitting chains takes time and pulls buses from service. Suddenly, 5 minutes becomes 40. Service frequency plummets. A positive feedback loop feeds on itself. Reduced bus service pushes more people to drive, which clogs roads and slows remaining buses. Negative feedback loops are stabilizing, actions that push systems back to normal. As traffic worsens, some people work from home, reducing cars. But these decisions act more slowly than the runaway loop. If the positive loop spins faster than stabilizers can correct, the system spirals until it breaks down. Crossing thresholds can trigger a new state where delays accelerate rapidly. If you're finding this useful, like this video, comment with a system you want us to analyze next, and subscribe so you don't miss future episodes. Next, we zoom out to the network level, where a single delay can travel continents. Modern systems are deeply interconnected networks. A delay that starts in one place rarely stays there. Consider a car. Over 30,000 parts from hundreds of suppliers form a complex network. A small factory in Malaysia producing a specific microchip has a fire. Production stops for 2 weeks. A local delay. That chip is critical for the engine control unit. Without it, the control unit supplier cannot complete assembly. Without the ECU, the car manufacturer halts the line. Dealers miss inventory, and a customer is told their car is delayed by 3 months. A 2-week delay cascades through the network, growing in duration and impact at each step. The tighter the coupling, the more parts depend on each other in real time, the faster and more violently cascades spread. The same connections that create efficiency carry the contagion of delay during a crisis. Small delays do more than make us wait. They are diagnostic tools. When a small disturbance creates a massive failure, it reveals hidden architecture, invisible connections, brittle points, weak buffers, misaligned incentives. Fixing the initial trigger is never enough. Patching only restores the previous fragile state. Real solutions change architecture, thoughtfully add buffers, redesign incentives, and build mechanisms that dampen disruptions. Resilience is not the absence of failure. It is the ability to absorb failure and keep functioning. How much efficiency are we willing to sacrifice today to avoid a catastrophic failure tomorrow? You've been watching System Atlas, exploring how the world's systems really work. Share your comments below. See you in our next episode.